So what you're looking at right now is, I suppose if you were being generous, you could call it a console application for Windows that I wrote in C++. And what it is essentially, as you can probably tell, is a spectrum visualizer for microphone audio. But in this particular mode, there's these pitch names at the top, and so you can actually use this as a guitar tuner. So if I were to produce a note by, for instance, whistling, you see that a spike appears in the spectrum, and so you can use that to tune a guitar by aligning the spike with the note names at the top. And one of the nice things about a spectrum visualization based guitar tuner is that you can actually tune multiple strings, because you can play multiple strings, you'll see multiple spikes, and you can align them without having to wait for the program to recognize the pitch every time. And you know, when I was doing this, there were actually several interesting things about pitch and intervals and octaves that I noticed, and so I thought it might make for an interesting video. So what I'm going to do in this video is I'm going to go over the coding of a simplified version of this tuner program, and then the full version will of course be linked in the description as well if you want to take a look at that. Okay, so as you can see, I have code blocks open here. Code blocks is good free software, I think, but there's there's obviously better options out there like Visual C++ and things like this that actual professionals use, but I don't have experience with any of those. Now, full disclosure, given my pretty rudimentary programming skills, I'm not actually going to attempt to do this from scratch live. I've written this program before, and as a matter of fact, I have it printed out next to me, and so I'm going to just essentially type it in live and talk about it. But I figured that way it will be easier to follow than if it's already typed out and I kind of just point things out. So as you can see, there's a bit of code on screen already. I have some libraries that I've included, including SDL. So SDL is the library that I'm using for audio, and if you don't know what SDL is, it's essentially a library that gives you access to various hardware on your device, such as joysticks and displays. It can do graphics and things like this, but I'm using it for audio here. It is also quite popular for audio. And then the other thing that you're seeing over here is an FFT function. So what is FFT? It's the fast Fourier transform. It is the algorithm used to take a signal and tell you what frequencies are in it. So this is a very famous algorithm, very important in engineering. And the thing that started this for me is that I wanted to learn about the FFT, and so I wrote an FFT function, and then I wanted something to use that in, and so then that's why I made the tuner. Now, do I recommend that you write your own FFT algorithm if you're just trying to make a tuner? No, because there's a lot of really good FFT algorithms written by people who put in a lot more effort than this. What I've done here is essentially the simplest version of the FFT, which is the recursive FFT. It's pretty slow compared to some other implementations, but I'm just using it and not using an external library because it's fast enough for my purposes. So I'm going to keep that FFT function minimized for the bulk of this, because it's really not the focus of what we're doing here. But if essentially what the FFT does is it takes an array of data, which is a signal, and then essentially, so let's assume for now that your the input to the FFT spans exactly 1 second of audio. Well, in that case, the first element of the output of the FFT would give you the magnitude of 1 hertz frequency, and then the second would give you 2 hertz, the third would give you 3 hertz, and so on. And if the length is different, then it scales accordingly. So again, that I'm not going to go into details of how FFT works. It took me a long time to understand it, and there's quite a bit of algebra involved. But what I'm going to do is just use the FFT to make a tuner. So the first thing I'm going to do here is define some things for our audio and the parameters. So the first thing is rate. This is going to be the sample rate of our audio. Then there is chunk. Now this is, I'm using the word chunk because I've used Pi audio before this, and that's what they seem to use there. What this is essentially is the buffer size. So I'll go ahead and put something like 128. This should usually be a power of 2. Then okay, so hash define channels. So this is how many channels of audio you have. So if you have stereo audio, the way it's represented usually in your signal is that you have one sample for the left and one sample for the right. So if you want to play it in stereo, then you have to split it apart like that, but we obviously don't need stereo audio, and so I'm just using mono. Now hash define format. So this tells us what format each sample is going to be in, and what you can do for this is you can use one of these flags that are inbuilt in SDL. So this is going to be audio underscore S16 sys, and what 16 sys, and what this means is that it is signed integers that are 16-bit. So it is 16-bit signed integers in system format. So system format here refers to, is it big endian or little endian. We don't want to be doing bit reverse or anything like that. Whatever is the system order, that's what I'm going to be using, so that we can directly store it into integer type variables. And then the next thing is hash define max sample value. Okay, so now this is going to be 32767. So this is 2 to the power of 15, and it is the largest value that a 16-bit integer can take. So given that we're using 16-bit integers for audio, we want to make sure that if we are our samples are never trying to exceed this value, because then what you get is garbage essentially. So then we have the next thing is define data len. Now this is going to be the length of the signal that we're going to be doing FFT on, and I'll go ahead and do 65536. So this is 2 to the power of 16, and it is the first power of 2 that is greater than 40,000, so that we can have frequencies all the way up to 20,000, because of the Nyquist theorem, which says that you need double the maximum frequency that you want, you need double the sample rate of that. So that's why this is this number, and it has to be a power of 2 because of the way the FFT works. Then we're going to do some type defs. So I'm going to say type def short sample. So short is a 16-bit signed integer, and so that's what our samples are going to be. And then type def. So as you can see, I've included this complex library over here, and so I'm going to define a complex data type, which is going to be std complex double, and I'm just going to call that cmplx like that. Okay, so now what you're going to do is define an array that's going to contain the actual audio that we're going to FFT, and this is I'm just going to use a global variable. In the full version I've used a queue and things like this, but let's keep it simple here. So sample current audio data len. Okay, all right. And now the other thing is the position in this array that we are going to be writing new audio to. Okay, because if you have fewer than data len samples coming in at any time, you don't want to end up with a partially filled array. And so what we're going to do is we're going to say int write pause equals, we'll initialize that to 0, int, and then as we write new data into our array, we are going to increment write pause so that new data can be appended to that, and we don't end up with a partially filled array. Okay, so now what I'm going to do is I'm going to define a callback function. I'll come to what a callback function is, but there's a particular syntax for this, which is like that. So so now what is a callback function? So essentially when we're doing audio, most sort of audio libraries, the way they work is with callback functions. So in this case, we're going to be using the audio card for recording audio, for getting audio from a microphone. So what's going to happen is whenever the audio card has new data, it's going to call this callback function, and then what it's going to do is it's going to put the data at this location. So this is a pointer, and at that location in memory is going to be the new data, and then stream length tells us how many bytes of new data there is. And so now what we're going to do first is we're going to say sample star new data equals and then so the stream this is 8. I'm sorry, this is uint 8. It's an 8-bit integer, a pointer to an 8-bit integer. So it gives us a pointer to an 8-bit integer, which is the first byte of the data. So it's giving us a pointer to the first byte of the data. However, our actual data is in the format of 16-bit integers. And so what we're going to do is we're going to typecast this 8-bit integer pointer into a 16-bit integer pointer by saying sample star stream, like that. And then we'll say int num samples equals, so this length, stream length, is a number of bytes, so we're going to divide it by the size of a sample to get the number of samples. So we have stream length divided by size of sample, like that. Okay, so now we're going to iterate through the incoming data and copy it to the output, which is our current audio array. So for that's, we have copied one sample, and then what we're going to do is we're going to have to increment write pos, and so we say write pos equals, and then we say write pos plus 1, but we can't leave it there, because if we do this, what's going to happen is eventually write pos is going to become greater than data len, and then we're going to be writing outside the actual allocated memory. And so what we do is we just put modulo data len, like that. And so now once it fills up, it's going to start writing at the beginning again. Okay, so that's our callback function. And all it's doing is it's constantly taking audio from the microphone and putting it into our current audio array. I'll go ahead and move this type definition next to the other type definition, because there's no reason to do otherwise. All right, so now one thing about the FFT is that it operates on complex numbers and gives you complex numbers. Now that is not ideal for us, because our audio obviously is integers, which are real, and we also are not really worried about the phase of the different frequencies that are in our signal. We just want the magnitude or the amplitude. And so what we're going to do is we're going to write a function which takes real input, converts it to complex numbers, does the FFT on it, and then takes the output, which is going to be complex, and again converts it into real numbers and gives us the real output. So I'm going to call this void find frequency content, like that. The input arguments to this are going to be a pointer to the output array, where the the sample outputs are going to go. Now, okay, so this might be a bit confusing. Why am I using sample for the output when I'm actually going to be outputting frequency coefficients? Well, it just works. So that's why I'm doing it. And it's quite common to think of frequency coefficients and audio samples being the same data type. So you can do it that way. Now, if you want the output to be a different data type, that is fine as well. But I'm just going to be using the same data type as the samples in this case. And then sample star input. And now these are actual samples. I'm sorry, this needs to be a comma. And then the next one is the length of the input data. All right. So now what we're going to do is we're going to create complex arrays equals new cmplx n, and then the output like that. Okay, now we need to do the FFT on it. We just iterate through our input and convert each one to a complex number and store it in FFTN. So now we're going to actually perform the FFT. So I'm going to call the FFT function FFT out, FFT in, and n. So now our FFT is done, and the data is in FFT out. What we need to do is convert FFT out back into sample data type. So again, we just iterate. So what I've done here is I've taken the absolute value of the ith complex number, of the ith output, and I've stored it in a double, okay, called current value. And one of the reasons for this is because you cannot directly convert a complex number to an integer. C++ doesn't allow that, and so you have to convert it to double first. And the other reason is because you want to make sure that whatever this value is not greater than the maximum allowable value in a sample, because otherwise you'll get garbage. So what I'm going to say is output I equals sample, and then what I'm going to put here is I'm going to say if this current value is greater than the max value, then use the max value, otherwise use the current value. Okay, so essentially what I'm doing is I'm clipping the output by using a conditional operator like this. All right, and then what we need to do is delete the new arrays that we created. So I'll say delete FFTN and delete FFT out, like that. So that is our find frequency content function. What this is going to do is it's going to take our input audio and it's going to tell us how much of each frequency is in that input audio. So now we come to our main function, and right off the bat you might notice something somewhat unusual, which is that the main function is taking arguments. So a lot of the time the main function doesn't take arguments, but as it happens, it is perfectly fine for it to take arguments. And SDL actually likes to pass arguments to the main function. I'm not entirely sure what their role is, but these are the arguments that the main function must accept to be used in SDL or with SDL. The first bunch of code that we're going to write is all SDL related, and it's going to be initializing audio in SDL and starting the audio device, starting recording and things like this. Okay, so the first line is SDL init. This is a weird capitalization, but whatever. And then we say SDL init audio, init audio like this. So SDL init audio is a flag defined in SDL that tells it to initialize just the audio, which is all we're going to be using. You can also do SDL init everything, that works too. Now there's a class called SDL audio spec, or perhaps it's a data, perhaps it's a struct, I'm not entirely sure, but this is defined in SDL, and you need to create objects of this type or structs of this type in order to pass to SDL to tell it essentially the kind of audio that you want to use. So all of these variables that we defined up here, or rather these, we're going to store all of these in this audio spec object, which I'm going to call rec audio spec. And so I'll go ahead and do that. Okay, so now we have this rec audio spec object that we're going to pass to SDL in order to tell it to open an audio device and have, and attempt to open it with these parameters. And so the function to open an audio device is called open audio device, which is a good name. And what you need to do is you need to assign the output of that audio device to a variable audio device ID. So now we have opened our audio device. Most of these parameters, I'm not entirely sure what they do, but obviously we have passed our audio specifications, our desired audio specifications to it, again, little s. And this one over here means open the device for recording. If that was 0, then it would open it for playback, which is, I believe, the default. And so now what we're going to do is we're going to go ahead and start the audio device. And the way you start the audio device is by telling SDL that the audio device is not paused. So you use the function pause audio device, and you say rec device, and this is why we needed to assign this over here so that we can have a handle to this device. And so now we pass this handle over here and we say 0 to not pause, or in other words, to start. Okay, so now we are recording, and every point here on in the execution we will always have audio data available in current audio, because the callback function will be continually called and the audio will be refreshed. So now what you're going to do at the end of the program is close the audio device like this. Between this line and this line is going to be the logic for the guitar tuner. Okay, so now the first thing I'm going to do is define the string that appears at the top of the screen showing the pitch name. So I'm going to call this char pitch names. Now in the full version of the program, that string actually dynamically changes length as the console window changes length, but I'm not going to do any of that over here. I'm just going to make it constant, and I'm going to say A, and then I'm going to put 3 spaces, and then I'm going to say A hash to approximate A sharp, and I'm going to put 2 spaces, and then I'm going to put B, 3 spaces, C, and so on. And then I'm just going to end it with a new line character so that it goes to the new line after printing this. So now if you look at what's happening here, we have a letter name, and then we have 3 spaces, and then we have another letter name, and now we have a hash symbol, and then we have 2 spaces. So essentially for each letter name we have 4 characters, and so the width of our tuner display is going to be 48 characters, right? So what I'm going to do is I'm going to make an array of integers which is going to contain all of the heights of the different, there are going to be 48 bars in a histogram essentially, and this array called bar graph is going to store all of those values. Here's where the sort of interesting musical stuff begins to enter the picture. Over here, essentially, what we're doing is we're spanning an octave, right? And what we're going to be doing is we're going to be dividing this octave into 48 bars of an histogram. Some of you might know that an octave corresponds to the frequency ratio of 2. And so if you have an octave divided into 48 equal parts, then each of those is going to correspond to an interval of 2 to the power of 1 by 48, or in other words, the 48th root of 2. And so I'm just going to calculate that here because that's a number we're going to be using. So this is our interval between between the frequencies represented by each bar in our output histogram. So we have our intervals and we need a reference pitch. If we have reference pitch and we know the intervals, every pitch is defined. So the reference pitch is going to be A1, and A1 has a pitch or a frequency of 55. Pitch A1 equals 55. Okay, so this is the pitch of the note A1. If you don't see how that works, it's A4 is 440, half of that 220, half of that 110, half of that 55. So the pitch of A1 is 55. And then what we're going to do is we are going to create we already have an array with audio. What we need to do is we need to create an array that will contain the frequency coefficients, right? So that we can call our find frequency content function, pass in the audio, and then we can get the output, right? So we need to create this output array. So I'll call that spectrum. Okay, so now what we're going to do is we're going to create a loop, and this is simply going to be the main loop in our program, because if you noticed earlier, it was continuously finding the spectrum and plotting it. So this is that loop. Within this loop is going to be the code to find the spectrum and plot it. And I've just put 100 over here for this thing to happen 100 times, and then the program stops. So within this, what we're going to do is first we're going to find the frequency content. We're going to call our find frequency content function. So now the next thing we're going to do is we're going to iterate through all of the bars in our histogram and calculate how much of that note is there in our input signal. So we're going to iterate through 48 bars, and the way this is going to work is that essentially for each bar in our histogram there are actually multiple frequencies corresponding to that. So for example, to the bar corresponding to A, we're going to look at A1, but we're also going to look at A2, which is the frequency an octave up from A1, and we're also going to look at A3, which is the frequency 2 octaves up from A1, and so on. So first we're going to initialize the value of this bar to 0, and then we're going to go through all of the different frequencies that correspond to this, and we're going to iteratively add onto this 0. So the first thing to do is calculate the frequency corresponding to this bar, the first frequency corresponding to this bar. So that is given by the pitch of A1 times how many ever 1/40th of an octaves up this current bar is, right? So the frequency corresponding to this bar is J 40ths of an octave above A1. Right, so that's what we're doing here. Then what we're going to do is we're also going to find the next frequency, and the reason we want the next frequency is because we're going to average everything from this frequency to the next frequency and plot that. So essentially we're going to have a spectrum that has a resolution of 1/40th of an octave. Okay, so now that we have calculated the frequency corresponding to this bar, there's another thing we need to calculate. So remember that the first frequency coefficient in this does not necessarily correspond to 1 Hertz. In fact, it doesn't correspond to 1 Hertz, and the reason is because our sample rate and the length of our data are different. And so we need to do a mapping to take the frequency that we actually want to look at and find what index in spectrum corresponds to that frequency. And so that mapping is essentially given by dividing the two like this. Now, one thing you might be thinking is kind of weird is, why am I using a float to store an index? And the reason is because actually the difference between two indices might be less than 1, because we're also going to be looking at octaves. That difference of less than 1, when it's multiplied by 2 and 4 and so on, that might later become greater than 1. So we need to actually keep track of the fractional part of the index, but when we use it for indexing, we're going to round it to an integer. And just like I found the next frequency, I'm going to find the next index. Okay, so now let's just kind of go over once again what each of our loops is doing. So this loop is just the background loop of look at like record audio, analyze, plot, record audio, analyze, plot. Okay, so this is the background loop of our program. This loop is iterating through bars in our histogram. Okay, but now for each bar in our histogram, we're going to be looking at multiple octaves of the same note. So now we need a loop to iterate through octaves, and what I'm going to do is I'm going to iterate through 8 octaves, because if you think about it, that is beyond most notes that we are going to actually be playing on instruments. So now for each octave instance of each bar, remember that we are not only looking at one element in spectrum. This is because spectrum has a very large number of elements. Spectrum has data len elements, and data len has 65,000 something. whereas we are only mapping to a total of 48 bars, right? So this means that if we're looking for the particular frequency that corresponds exactly to one of these bars, then there's a good chance that we will miss a spike that is, you know, a couple of indices to one side or the other. And so actually what we need to do is we need to find an average from one bar to the next and use that average as the value. And so what I'm going to do is I'm going to iterate from the current spectral index to the next spectral index and find the average. Alright, so what we've done here is we're adding the actual frequency coefficient divided by 8. We're dividing by 8 because we're looking at 8 octaves, so we want the average across all the octaves. And we're also dividing by next spectral index minus current spectral index. So this is the total range of indices over which we are averaging for the current octave, right? So for each octave, we're dividing by this to average over that, and we're also dividing by 8 because we want to average over 8 octaves. And then we have to multiply the spectral indices by 2 to go to the next octave. Alright, so this is essentially the main, you know, signal processing of the guitar tuner done. We have 48 bars in a histogram, each of which tells us the pitch corresponding to that bar, how much of that is present across 8 octaves. So it's octave-wrapped logarithmic scaling on the x-axis. So now all that is left to do is actually print out the histogram to the console. So the first thing I'm going to do is I'm going to use system CLS to clear the screen. Now I know that you know, professional software developers don't like this command because it's unsafe and things like this, unsafe in a security kind of way, and it also is computationally not very great. However, I don't think there's really a better way to achieve what I'm trying to do, and for, you know, little hobby kind of programs, I'm sure it's not an issue. And so then we're going to first clear the screen, and then what we're going to do is we're going to display the pitch names across the top of the screen. So I'll go ahead and say std cout pitch names. And now what we need to do is we need to iterate through a matrix essentially and look at each point in the matrix and say, okay, so do we need to print white space here, or do we need to print whatever character we are using for our histogram? And so I'll go ahead and code the nested loop. So what I'm doing here is I'm actually iterating downward through the rows, because obviously this is going to be printed top down. That's how consoles print. And then I'm iterating top to down through the rows, and I'm iterating left to right through the columns. And for each point, I'm going to say, so if the value of the bar graph at this point is greater than the current index, the current row, then print an equal to sign. And so this is how you get solid bars with equal to signs in, you know, vertical columns, filling each vertical column. However, there is something you need to keep in mind here, which is that the actual value of bar graph is way bigger than 48. And so we'll go ahead and multiply this by some large number. I've tried this before and 200 works, so that the comparison makes more sense. And then I'll say else print white space. All right, and then that is the end of the current row. And then before we go to the next row, we need to print. And I will actually, so I've been printing strings. I'll make those characters because I think it's a bit faster. All right, so that, I think that's it. That should work, because what we have done everything we need to do. We have looked at each bar in this bar graph and found all the corresponding frequency coefficients and added them to them and averaged over them. And then we have, you know, printed out the pitch letter names at the top, and we have printed out the actual histogram. So let's see if this runs. Okay. And SDL, I wrote Claude audio device, so that, and let's see if this runs, and there you have it. So that is a simplified version of the tuner, and it's a square display. You can resize the console so that it sort of fits. Oh, okay, it went through 100 iterations. Let's run it again. Yeah, so that's that. You can you'll find a link to the full version of the code, which has other kinds of visualizers too, in the description. It's on GitHub, and I also have a compiled version, so you can just download it and run it if that's what you want to do. So this is the full version of the code, and as you can see, there's actually several different options here. So the last two are guitar tuner modes, but the others do other things. So if I say fixed semi-log, then I can put in frequency limits. So if I want to visualize frequencies between say 100 hertz and 20,000 hertz on a semi-log scale, then I can go ahead and do that, and you can see that this is a visualizer. Yeah, that's a visualizer. All right, hope you enjoyed that. Hope you found some of these things interesting about the the octave wrapping and intervals and things like this. It was a fun project for me. Okay, bye.